Okay, thank you. Hello, everyone, to the third session of the conference, the Quantum Science Conference. It's really nice to see so many participants again this afternoon. I was able to also join a couple of talks, and there's also so many, so thank you all for coming. My name is Robert Fickler from Tampere University, and I'm happy to chair this session. And without further ado, of course, let me introduce the first speaker, which is Andrii Semenov. I hope I pronounced it correct, from the Bogolyubov.
Absolutely.
Very good. From the Bogolyubov Institute for Theoretical Physics. Yeah, so with he will talk about today about photon counting measurements with realistic photon number resolution, which I'm really interested to hear. So Andrii, the stage is yours.
So thank you very much, Robert, for introduction. And first of all, I would like to thank the organizer for inviting me for such a great event. Some talks are really impressed. I hope I will not disappoint you with our results. And with my talk, I'm going to the field of quantum optics, as you can see from my presentation, which is a basic branch of science in principle in quantum information technology. But before I start my talk, let me introduce my co-authors. So a lot of part of my talk has been done with my co-author Vera Uzunova, who is now in the University of Warsaw. She is there from the start of the war in Ukraine, but actually she's from Kiev. Also, a lot of discussion work has been done with Professor Boris Hage from the University of Rostock in Germany. To my other co-authors, Professor Werner Vogel from Germany and Professor Andrei Klimov. I enjoy really discussions with them, and some paper has been published with them also. And three our master students, Vadim Kovtanyuk, Ivan Yeremenko, and Victoria Lень, who is now in Weizmann Institute, have also significantly contributed in these results. So as you can see from my talk, I'm going to talk about, from the title of my talk, I'm going to talk about photodetection theory and realistic photodetection. And this is a basic measurement in quantum information technologies, including quantum universal, non-universal computing, quantum communications, quantum metrology, and also it plays a crucial role in many basic quantum experiments. Of course, theory of photodetection well known. For technological application we need it, but unfortunately our work is not perfect. Sometimes it's terribly imperfect, yeah. And we need to adapt our theories to real world applications. So this is what I'm going to speak about today, because my talk is supposed by organizers, suggested by organizers to do for the broader readership. I remind you some very basic textbook things from the photodetection theory. After that, I will talk about our recent theories that we have done for superconducting nanowire single photon detectors, which are now very popular and widely used in quantum information technologies. So, and after that, I will present some elementary application. Okay, let's start with basic things. Yes, with very basic things about photodetection theory. As you all know, there is no purely classical photodetection theory, because photodetection process is based on photoelectric effect of light, and at least detectors should be described as a quantum object. In principle, so this is why we say about semi-classical photodetection theory. In principle, we can consider photodetector as a huge number of atom-like systems, yes, and this radiated by light with complex amplitude alpha, or with intensity model alpha square, and some electrons are excited, some atoms are excited in somewhere in a universe of perfect photodetectors, you can apply voltage and count the number of these electrons, which we call as photocounts. So basically, photodetector is something that invert your light intensity to the number of photons. This process is stochastic because device itself is quantum, yeah, and probability distribution for photocounting distribution for, in this case, is well-known Poisson distribution. First imperfection appears even not from the device itself, but from the light, because even in classical theory, this can be stochastic and described by the probability distribution rho from alpha. So in this case, you should integrate it and you get a well-known photocounting formula. In quantum case, you can start or you can describe your discussion. This is already not photocounting. So in very, very perfect situation, this is number of photon, and this is described by the well-known Born's rule, well-known from the textbooks on quantum mechanics, where n is rho is density operator and n is Fock state. And here you can say about probability distribution for the numbers of photons. What is interesting that you can invert it, it's well-known things in the normal ordered form. So this resembles somehow for us Poissonian distribution. But even more, as it's well-known from the quantum optics, density operator can be expanded by projectors on coherent states. Here, this is P function, Glauber-Sudarshan P function, and you can simply substitute it here. And to get another presentation for photocounting equation in Glauber-Sudarshan presentation or in phase space. So you basically have, two equations. You basically have two equations in operator form and in phase in Glauber-Sudarshan per representation. Yeah, what is interesting that photocounting equation in Glauber-Sudarshan presentation resembles classical photocounting equations. Yeah, but P function should not be positive definite. It can also be negative. Yeah, and I will speak about it a little bit further in my presentation. But at the moment, it's for us, it's important that this is the same as classical things. Yeah, and this is all that I want to stop with this ideal world. Now we are going to our realistic universe, yeah? And in our realistic universe, we should replace this projection operator or this Poissonian distribution, yeah, with another operator, yeah, which calls positive operator value measure. It is POVM. This POVM describes photocounter, photodetection process. For each photodetection process, we have its own POVM. Actually, we can also use here Glauber-Sudarshan presentation. In this case, we have such a nice formula, yeah, that here you have these POVM symbols, as people sometimes say. And for these POVM symbols, there is very good physical interpretation. This is simply probability to get n photocounts given amplitude alpha or coherent state alpha. So this is practically the same, very good. So we have very good interpretation for these things. It is also sometimes called as a seems as a classical response function. And please see that this function is always positive definite. Yeah. Some examples, first elementary examples, which all of us know when we have detector with some finite detection efficiency and duck count rate. So something can be scattered or absorbed. Yeah, this is modeled by beam splitter. Also, we can have some additional noise as duck count, so this is not interfering like modes. And in this case, you can simply add eta n, replace n with such a combination eta n plus nu. Yeah, and you can get this equation. So this is a little bit closer to a real application, but still far away from our reality. Why? Because today detectors mostly, so far as I'm a theoretician, yeah, okay, as I can understand, so detectors cannot perfectly distinguish between numbers of photons. Most detectors can only tell you that either photon exists or does not exist, but they cannot tell you how many of these photons. And this is described by such a POVM. So it has only two components, off or on. So in principle, this equation is very, very realistic. Yeah, okay. But for sure, this is not we want to have in our quantum technological applications. So this is why people are trying to develop some experimental technique in order to get photon number resolution, at least approximately. And first step, not maybe first historically, but first step which we can understand is so-called array of n of detectors. Yeah, so you can split your light beam in some n, capital N, small modes. Yes. And suppose that each mode contains at least one photons, and after that to consider that the number of click detectors correspond to the number of modes. In this paper by Jan Sperling, Werner Vogel, and Girsher Gavar, POVM for this case has been presented. Please note, I do not write any more efficiency at the counts because this is trivially, each theories can be trivially extended to this case here. But nevertheless, this is not Poissonian distribution. This is somehow like a binomial distribution. And as it is shown in this paper, for real application, the result can be very different from what we expect to see in our from the idealized theories. Another story. And this is, as to me, a quite interesting story that I want to speak a little bit. This was maybe a very old application of detectors. This is when we have some measurement time interval and simply count the number of counts in this time interval. It would be perfect for the detection, because so the number of these pulses would be perfectly correspond to the number of photons, but there is one very not really nice point, dead time of detectors. During this dead time, photons cannot be detected. Yeah. And in order to, in principle, in order to exclude if effect of this measurement time interval on the next time interval, here we should have some interruption. So we should darken our detector, yeah, input. So for the counting equation, or POVM, or that time this was not POVM, was is known for a very long time, from 1966, I believe, first papers. It looks like this, yeah. And what I'm going to speak about is actually this technique, but in application to superconducting nanowire single photon detectors. So in this case, this technique has, so this is not simply dead time, will be dead time, but will be something more difficult. And because superconducting nanowire detectors are now widely applied, we believe this our theoretical work would be quite interesting for experimental people and for those who is doing who is working in this direction. So before I start with our theory, let me remind you what is superconducting nanowire single photon detectors. Actually, this is nanoscaled wire, yeah, where we have some superconducting current, which is really close to critical one, yeah, to critical one. And here we have some bypass with some resistance. So normally this resistance does not work because this is superconduction mode and current is simply circulating in this direction. What happens when we have one photon? So when one photon is absorbed, and this can be absorbed with very high efficiency for this superconducting nanowire single photon detectors, this a little bit hit this hits this point, so superconducting mode disappears. So this is not a superconductor anymore, at least in this region, yeah. and some current appears through this resistance. So you can see some voltage on this resistor, some voltage spikes. What is interesting here, I have a picture, a figure from this very nice paper by Natarjan and all in Superconducting Science and Technologies. This very nice review paper, by the way, on this topic. And here is described how all the things are going. So first you have detector in a normal mode. After that, photon is absorbed. So superconducting state is disappears. So here you have density of currents much more than density of currents appears to be more than here. So this appears to be because current here is more than critical one, and this to be hotspot, so-called, is increasing. Yeah. So it blocks finally. So this blue line here, this is like very quick process here. During this time, you cannot register any next photons. But after that, all current comes through the bypass, and detectors is slowly recovering to the previous mode. So this is this red line. And this is interesting that here we have normally somehow like a dead time interval. And after that, we have a probability to register a photon, but this probability is less than in this normal form. So we should take into account this relaxation process. So you can see that relaxation process can be really long here, so longer than that time in these nanowire detectors. Okay, what we consider, first we consider this scenario of independent time windows, yeah, for single photon nanowire detectors. We have some voltage pulses, we count them. We have some interruptions in order to avoid effect of this time window on the next time window, yeah. And of course, we have some things, so we should model this probability, this ability of detector to detect next pulse, to detect next photon. This ability we model with the detection efficiency, this time-dependent detection efficiency. We propose to have such a model because this model, so it looks like this dashed line, yeah, because here we clearly see a dead time interval and relaxation time. But actually, experimentally, it is more smooth curve, but our theory can be applied for any of these functions, see from tests or from any time-dependent efficiency. What we can do, so I will avoid technical details, of course, for this talk in order to not to bother you with such details. But we have derived the corresponding POM. This looks like this, yeah. So this is still photon number operator. So here we have time ordering integration. Yeah, it depends on this detection efficiency, time-dependent detector efficiency. And actually, if in the perfect situation, yes, it turns to normal this Mandel form to Poissonian distribution. One can easily check it because this is just time-dependent, time ordering integration. So this is 1 over n factorial. It's no problem at all. And this is nice story. In this case, it works, but when you speak with experimental peoples, nobody care actually, at least from my experience, about this interval, that what should darken this interval after each time window. Let's consider what happens in this case. In this case, we will have effect from, for example, from in this time interval with the number L, from the time interval from L-1, and also theoretically from previous time intervals. So we have considered this problem. This problem, in this case, because you have such a function, we should modify even photocounting equation. So this is not only POM, but even photocounting equation itself should be modified because here all modes are supposed to be the same. Yes, and here we have nonlinear dependence on the photocounting statistic on the density operator. The same story can be written in phase-space representation. So for this multi-mode POVM, we can write such an equation. And this equation is given in Markovian approximation. This means that we consider that for L's mode, there is effect of L minus 1s. For L minus 1, there is effect only for L minus 2. So L minus 2 cannot directly affect on the L. And even we have supposed a little bit more serious approximations that because we suppose that there is some time delta where everything works. And multi-mode application understands that this equation is a little bit complicated. Multi-mode, this memory effect from previous time intervals is given here by this function, which has very nice structure. For example, here is first term. This is effect of previous time interval. This is effect of 2 previous time intervals, 3 times intervals, and so on. So this is actually very similar to what we have in any Markovian theory. Okay, this is what we have in this. So like I said, real world application modify for us not only POVM, which one could explain, but also photocounting equations. So this one should take into account for quantum optical application or quantum information application. Now, I will like to show you some examples, of some quantum states. For example, this is coherent states. So what happens with coherent states when we have, for example, this rain histogram? This is some Poissonian distribution for ideal photodetector, photon-number-resolving PNR, photon-number-resolving detectors. This is when we consider no relaxation time, but relaxation time model simply like a dead time. After that, we have like an independent measurement time windows. And this green line is for memory effects. So you see, all of them are really different. And for some remarkable quantum states, for example, for Fock state, we have such situation. For attenuated Fock states, also very different. And also for squeezed vacuum states, we have different situation. So even memory effect here may be not so significant in this case, but also should be considered. It should be taken into account. So in real applications. And now I would like to demonstrate some things, some applications of our theory. And first of all, what I would like to say about is non-classicality of photocounting statistics. What is non-classicality of photocounting statistics, at least from my point of view? Okay. So this means that you, for example, you have some light, So look at this equation for the counting way. You have some light, and if your P function is positive definite or non-negative, then you can always simulate these statistics with statistical mixture of coherent states, which are considered as an analog of classical pure states. But if P function is not positive definite, you may not simulate this statistic. So statistic may have some properties, sometimes may have some properties which are impossible to simulate with classical light. So this means that this is a mark that this can be used in quantum technologies, for example, And the most well-known, maybe first method for testing this non-classicality of the statistic is Mandel parameter. So it's presenting like this, and this well-known. When Mandel parameter is negative, then we have so-called Poissonian statistic of light. And so this photocounting statistic is non-classical. Mandel parameter has at least this method has at least 2 disadvantages. First, it is valid only for ideal photon number resolution. And second, it does not work for all non-classical statistics. First disadvantage was resolved for For example, for array detectors, in this paper with Jan Sperling, Werner Fogger, and Pirsh Agarwal, they have presented a binomial analog of Mandel parameter. And it really good works because even it was in the group of Professor Wormsley where some experimental verification of this method. It really works, so one can use it directly instead of Mandel parameter. For second disadvantage, that it does not work for all things. So unfortunately, cannot be second disadvantage, second problem cannot be resolved with this method. Okay, we have proposed our method, how one can deal with this problem. Look again at this equation, yeah? And this equation we consider as an integral equation, where p function we consider as a known function. Of course, you can tell me that to solve this equation is very difficult because solution of this equation, first of all, is not unique. And this is true, especially for phase-sensitive light, yes. Another story here, we have experimental data, so it is almost impossible to resolve this problem. But we are not going to solve this equation. We are going to answer the question, either this equation has non-negative solution. When it has non-negative solution, then this statistic can be simulated with classical states. So it has nothing with, this statistics has nothing with with quantum optics. And we use here some logic, some deep connection with Bell inequalities, because in Bell inequalities, well-known problem with Bell inequalities, there is very, very similar problem. It is in more details discussed in this paper, yeah? And we have here such a theorem that existence of non-negative p function, in order to this non-negative function, p function exists, it is necessary and sufficient that for any sequence lambda n, which we call test function, such inequality is satisfied. So you can choose lambda n, some test function. After that, build left part. What is left part? This is, in fact, some mean value of this lambda for quantum light. And this is right part, is mean value for classical light. And when you find such a lambda that this inequality is violated, then you cannot simulate your statistics with statistical mixture of coherent states. In order to do it, to be honest, we even do not need to know analytical form of Pn from alpha, because this we can obtain from the classical quantum data, and this we can clearly obtain from classical data. This is from quantum, this is from classical. And if this inequality violated, so this is what we need actually. And let's see how it works. First of all, first states which is non-classical but has positive Mandel parameter is even superposition of coherent state. With perfect detectors, this is violated, it is clear. And with array detectors, we have shown it's also violated for some reasonable parameters. I will not now say about details. Details can be one can see details here in this paper, and it is also violated. To be more specific, for more special, more realistic situation, for example, is given by squeezed vacuum state. Yeah, for squeezed vacuum state, it is also, so it's easier to get experimentally. It is also known that Mandel Q parameter is positive definite for this state. So for perfect detector, it would be violated, this inequality. For array detectors, it is violated. And even I can show you what happens, even not for squeezed vacuum states, but for phase randomized coherent states. It is supposed that such states does not have non-classical photon number statistics because it has non-classical statistics for the phase. Nevertheless, it still has, and it can be checked even with superconducting nanowire single photon detectors. So here you have seen in these plots right-hand side of inequalities. This is left-hand side. So this is maximum part of this, and you still have here some gap. So this is for more or less given practical parameters. So we hope that in this case, one can violate this inequality and confirm that non-classicality of photocounting statistics exists also for such states. Yeah, for phase-squeezed coherent states. Okay, a little bit another application, Hong-Ou-Mandel, well-known Hong-Ou-Mandel effect. We have 50-50 beam splitter, and each input port of this beam splitter is irradiated with single photons. We have such input-output relations with transmission and reflection coefficients. And this is well known that, for example, in classical theory, when we consider our photons as classical particles, so the probabilities to find photons, for example, in both detector would seem like looks like this. In one detectors looks like this. If we consider photons, so not like distinguishable particle, but like bosons, we have totally different equations, and this is well known. For example, when T is equal to R, so this will be 0. So so probability to get both photons in these detectors will be 0. So they will go only in this direction both, or in this direction both. Yeah, this is actually the essence of the Hong-Ou-Mandel effect. What happens if we have such detectors with imperfect photodetection? In this case, so here I still with this light green color still ideal PNR our formula for photons. And this is what happened for realistic PNR detectors. So you can see that each of probability is like this. So here is calligraphic P is new probability for realistic detectors. This is old probability, but multiplied with some factors. Yeah. Here, this factor can be calculated like this, and this actually has a physical meaning as a probability to get n clicks given n photons. Very interesting to see what happens, for example, when this is just losses. When it's just losses, these factors in all three cases is eta square. So detection efficiency square. So you may forget about this problem by simple post-selection. But this is not the case for a more complicated situation, for example, for array detector, because you can see that here this is 1, and here it differs from 1. So it scales differently with other numbers. And we can go to more complicated scheme to generalize Hong-Ou-Mandel effect. So this scheme is often used in boson sampling, in standard boson sampling. And we can consider what happens if in this scheme we will have such detectors with imperfect photon number resolution. Yeah. In this case, the same story. We have some correction coefficients, and here is some dependence of these correction coefficients. For example, here for array detectors, so this is as a function of the number of detectors in array. And here, this is for detectors with that time, this as a function of that time. And an interesting story is that in principle, yeah, we cannot say that we can directly apply it for boson sampling scheme, because in boson sampling scheme, you know, one interested only in collision-free regimes. Yeah, and so it's enough to have collision-free regime. But so this is actually what happens for generalized Hong-Ou-Mandel effect. But nevertheless, I still see some connections with boson sampling scheme and some useful thing for boson sampling scheme here. And let me comment about it at the very end of my talk. And now I just present you what we have, for example, for a more realistic boson sampling scheme. Again, please do not consider it as a boson sampling, simply like boson sampling, simply like interference experiment. So when we have at the input Gaussian states. So in this case, very well known, for example, equation is that probability to get these photons is written like this. And this is actually some characteristic of this Gaussian state. This is covariance matrix for Q function. Yeah, and everybody knows that this can be expressed as a Hafnian of this matrix A. That is difficult to calculate. So this in theory, in graph theory can be calculated, and this is to calculate this is a computationally hard problem, and also its computational hard problem is to sample this random events from these probabilities. And for on-off detectors, when we have here, there is, so this is more practical situation, which is actually used in experiment. We have such equation, which is expressed in terms of Torrentian. And what we were able to do, we were able to generalize this equation for any kind of, for this equation for any kind of detectors. This looks like this. And this formula is, so we hope will be useful for future analysis. And of course, one should think about whether this is useful for real boson sampling application, because still boson sampling application, we do not consider collision events. But in Gaussian boson sampling, it seems that without collision events, impossible to do something. Yeah, and in order to give some outlook for our things, I will show you maybe some applications why this can still be useful, why our analysis can still be useful. We were impressed with this paper, yeah, by Rahimi Kashari, Saleh Rahimi Kashari, Kim Ralph and Caves, yes, in PhysRefX. And where it has been considered optical networks. So you have some, so not necessarily linear, by the way. Yeah, so you have here some quantum states, you after that have some quantum channels, and after that you measure something. And the question is, either you can simulate this scheme with a classical model. Of course, to answer this question in general case, it's very difficult. But there is a nice theorem which tells you when classical simulation model exists. This theorem has been formulated here, and it is based on such a presentation, so phase-space representation of this equation, where there exists such S parameters, so ordering parameters S, that all constituents of these equations are positive definite, then classical simulation scheme exists. With our analysis, we think that we can apply this equation. So a realistic POM, we can apply, for example, our method of our Bell-like inequalities, and at least we can exclude some classical simulation models. So not all of them, but at least some very definite classical simulation models. Okay, now I'm going to conclusions, and this is so what we have reported, so what I have reported in this talk. So first of all, this related to we have obtained photocounting theory for the single-photon nanowire, for superconducting nanowire single-photon detectors. So we obtained Bell-like inequality for non-classicality of photocounting statistics, and consider some application to photon interference and quantum optical networks. This is some papers, some of them are not, even not in archive, because we didn't have a time due to stories that happen in Ukraine. Sorry, maybe I will post it in a near time, or just to wait for referee report. And after that post, And at the end, let me introduce my group. So this is, as you see, myself. Here we have a group of postdocs from the institute. So our group actually consists of two subgroups. One subgroup in the Institute of Physics. So this is the three postdocs: Alexandra Klishnichenko, Yevgen Stolerov, and Vera Ozunova. She is presently in the University of Warsaw. Four master students: Vadim Kovtanyuk, Ivan Yeremenko, Mikita Yurin, and Victoria Len. Victoria is now in Weizmann Institute. Our project was supported by National Research Foundation of Ukraine. So unfortunately, funding is now stopped. We hope that this is postponed. And I have to say that even more important than money, so we have, I should mention that we have protection for armed forces of Ukraine, because literally they saved our life here, because if we do not have such a perfect work of these guys and they're sacrificing, maybe we would not exist anymore. So thank you very much also to these guys who is now doing very perfect work, not only for us, not only for Ukraine, but I believe for the whole Europe. So thank you very much, and I'm going to answer your questions.
Okay, thank you very much, Andrii, for this really nice talk. And I agree. There's yeah, it's not just for the Ukraine. So, but let's not keep it. Let's keep it not apolitical here.
Yeah.
Thank you very much. So, is there any questions? I didn't see any questions in the chat here. Is there anything in the Discord? Akash, is there?
No, I cannot see, but maybe we'll have questions later. Yeah.
Okay, one question came up here. So from Muhammad, is it possible to measure polarization of a single photon?
Yeah, why not? When we always, when you see ours, when you deal with, when you're pretty sure that you have a single photon state, you do not need actually photon number resolution, all this stuff, because everything works for on-off detectors.
Yeah.
It's so all things, all interesting things appears when you have at least two photons state. This can be superposition, for example, or something like this. So polarization of single photons, yeah, why not? I do not see problem to me, because this is a standard procedure. Polarization analysis.
Mm-hmm. Thank you. Yeah, yeah. I also agree that it gets much more interesting as soon as you have more photons than just one.
Yeah.
But is there more questions from the audience? Feel free to type it, or maybe use then the Discord channel. So for the moment, there's none, but then I can ask mine that I have. Although I'm an experimentalist, so although you said during your talk that, yeah, you can look up the numbers there. So when you talk about realistic, like terms of efficiency or dead time, when can you expect that? Because you showed this non-classicality, when can you expect that the detectors, that's my understanding, that the detectors will wash that non-classicality out, that if the dead time is too long or the efficiency.
Of course. Of course.
Yeah.
Of course, but this is already not a science. This is already an art. You see, because our method. So I can show you. So you have with standard methods like Mandel parameters or even binomial parameters. By the way, binomial parameters this really nice things, but unfortunately it cannot be generalized to a more complicated stories for another detection techniques. But with all these our inequalities, yeah, you can in principle try. So this is actually optimization problem. I even see, I don't know, I'm not an expert, I even see that because this is Bell-like inequalities, so this can be perfectly, so this can be a nice task for quantum computers, by the way, yeah. But when you have, for example, detection dead time, detection efficiency, when it was non-classicality, you will have everything in this Pn from alpha. And actually, yes, in sometimes it can appear that positive definite solution of this equation exists. And when it exists from these inequalities, you can clearly see. Or better to say, you can always see that it does not exist. But this optimization problem, so solving optimization problem, my master student, Vadim Kovtanyuk, has really nice consideration of this story. And maybe we will publish paper about it because he has applied techniques that people usually use for all the story with Bell inequalities to this non-classicality problem. So it seems that this is more or less works, but okay, this will be washing.
Okay, thank you very much. Yeah, as an experimentalist, I mean, we see even these effects of that time when because nowadays we have so many photons in the photon pair source but we then usually when we go into this regime where this comes, we see that our measurement or our rates are changing, then we just crank down and we use less photons but I have to look into the theory of yours. Really, really interesting. Okay, we have another question from Akash. Maybe it was posted via Discord. So
in Discord. Can I read it? I don't know. So I'm not really familiar.
Yeah, actually, it is my personal question. So,
that's a personal question. Sorry, Akash.
Yeah.
So, are operator form and Sudarshan representation equivalent?
Yeah, of course. Absolutely. This is standard thing. So both forms. So when you have, for example, Q symbols or Glauber-Sudarshan functions, for example. So this means there is one-to-one correspondence between them. So this is absolutely not a problem. This known things.
Yeah, because I asked this because it looks like it is integral and this is like it is a summation, right? This operator form. So we need to have like n number of POVMs, which doesn't look like ideal, right?
No, but they are equivalent. This is now. There is another story. There is another story. Why can be non-equivalent? For example, when we say about this our method, of solving this equation, so solution may not be unique. So this can be not necessary when you try to solve this equation because this is not unique solution. This may not be necessary P function, Glauber-Sudarshan function, but something else which does not correspond to your real quantum states. And for example, you have, I don't know, squeezed coherent state, you use it here, and this is phase randomized. So then you will have a lot of other solutions for these equations, not only P function of squeeze, because here is the story of phase randomization. So this depends only on the absolute value of alpha. And in this case, you may get some solutions which are not, which do not correspond to density operator. But sorry, but when we consider from the point of experimentator measure this one, and the answer which experimentator can either I can simulate these statistics with statistical mixture of coherent states. When it exists, even in the case when this is not a Glauber-Sudarshan function of the real states, then you can simulate.
Okay, thanks for the answer. Yeah, that's detailed.
Okay, thank you again. I also have just came to my mind that the whole work, I guess, will become more and more important because from an experimental point of view, now there's cameras that are somewhat photon number resolving and special superconducting detectors that are also photon number resolving. So I think it's really interesting. Really, thank you very much.
Thank you very much.
Yeah, I will start.
Very nice to hear.
Okay.